In this video, we're going to finish the theorem that we started last time, which is that if f of x is a polynomial in f adjoint x, then f of x has a multiple root, a root of multiplicity more than 1, in an extension of f if and only if the polynomial and its derivate have a common factor of degree greater than 0 in f adjoint x. Last time we proved that if f of x has a multiple root, then it has to have a common factor of positive degree with its derivate, so now we'll prove the converse. So now we'll prove this direction. So let's assume that g of x is a common factor of f of x and its derivate of degree greater than 0. We're going to try to show that f of x has a multiple root in some extension of f. Okay, well, if g of x is a common factor between f of x and its derivate, then you might think a good place to look for a multiple root would be to look at roots of g of x, and that'd be a good instinct. So because g of x has positive degree, it has a root in some extension of f. Let's call that e. So some extension e over f. And furthermore, let's call that root alpha. All right, so g of x has some root alpha in an extension field of f. Okay, so then in e adjoint x, by the factor theorem, we know that x minus a, or x minus alpha, divides g of x. Okay, so since x minus alpha divides g of x, and g of x divides f of x, we have x minus alpha divides f of x. So let's go ahead and write f of x as x minus alpha times something. So f of x equals x minus alpha times, let's say, q of x for some q of x belonging to e adjoint x. Note that this has to take place over e because we don't even know that this factor x minus alpha exists in f. All right, so we have f of x equals x minus alpha times something. All right, so now we're going to try and use the fact that g of x is a common factor of both f of x and its derivate. So let's write down what the derivative of f of x is in terms of all of this stuff. Now, by the product rule, the derivative of f of x is equal to the derivative of x minus alpha times q of x plus x minus alpha times the derivative of q of x. All right, and the derivative of x minus alpha is just 1. So this derivative of f of x is equal to q of x plus x minus alpha times d of q of x. Okay, but look, we know that the derivative of f of x, this is divisible by g of x, by our assumption, and therefore also by x minus alpha, because x minus alpha is a divisor of g of x. And we also know that this piece, this term, is divisible by x minus alpha, because, well, there it is. So that means that because these two sides are equivalent, this also must be divisible by x minus alpha. Okay, so let's write that down formally here. Since derivative of f of x and x minus alpha, derivative of q of x, are both divisible by x minus alpha, q of x must be divisible by x minus alpha. So q of x is equal to x minus alpha times some other polynomial. Let's call that r of x. For some, a little bit more space here, for some r of x still belonging to e adjoint x. We have to do all this work over e. Okay, but then what do we know? We know that f of x is equal to x minus a times q of x, and q of x is equal to x minus alpha, sorry, a is alpha, x minus alpha times r of x. So f of x is equal to x minus alpha times q of x, and then substituting this, we get x minus alpha times another x minus alpha, r of x. So this means that alpha is a multiple root of f of x. Alpha is in that extension, and it's a multiple root of f of x. And so our argument is complete. If f of x and its derivative share a common factor, then f of x has a multiple root, and we are done.